developing small propulsion system entails a cost, let's say a capital expenditure, which is significantly lower than developing large propulsion systems. Because, you know, when you develop electric propulsion system, you need to test it. And usually the way which we tested it is putting them in vacuum. So you need to have a vacuum chamber that is creating the vacuum condition as close as possible to space. So of course, the chamber size goes with the thruster size. Testing a big thruster will take a huge chamber, which costs a lot. Of course, small companies could not necessarily let's say afford to have that. So these new companies are exploring different technologies. So let's say the consolidated market is now focusing on two major technologies, the Hall effect thrusters and the ion thrusters.
We are back with another episode of the Cold Star Project. I'm Jason Kanigan, the host and the founder of Cold Star Technologies. Today, I'm really excited to have on Riccardo Albertoni, who has a doctorate in space engineering. He is really into propulsion, electric propulsion. We're going to dig into that. And I wanted him on because he works with Airbus and is really getting into this propulsion system for the OneWeb constellation. So thanks for being here.
Thank you for having me this evening.
You bet. So yes, you're speaking to us from France. So Riccardo, I saw that you recently got your PMP, Project Management Certification. And I'm curious, what have you learned because of that you sort of wish you knew years ago regarding managing space projects?
Well, I think PMP has been very, very useful in a sense that it provides you with a very, let's say, good overview of all the topics that you are usually expected to work with as a project manager. So I'm talking about, let's say, eliciting requirements from the shareholders at the beginning, managing the shareholders, procurement management, risk management, all these kind of things. And it's very useful to create a common vocabulary between project managers or even in the framework or a team member of the program. On the other side, you know, when you work with in a big projects, you usually, I mean, the project manager usually is very supported by, you have cost controllers, you have schedulers, you have people that are acting on many of the specific topics. You have procurement managers. So I think at the end of the day, the most important thing for a project manager, especially when you are dealing with complex programs that are pretty big, is really focusing on the risk. So the risk of the programs and focusing on the team management. Communication is very, very, very key. And again, I think let's say the PMP gave me this overview of all potential topics, and give me also the metrics to discuss with other project managers and management of the company. But at the end of the day, I think at the end is the PMP is basically a test. So you study, you have your good overview, but you need to have hands-on experience. And the more complex the program is, the biggest is the number of your interfaces in the project, the more the hands-on experience, I think, rules over certifications.
Okay, so hands-on experience, very important.
Yeah, I definitely think so. On the other side, it's true that, for example, it depends on the maturity of the company in terms of project management. I mean, there are small companies in which the project manager is basically will do everything by himself. And companies in which, I mean, you have big support, and so the level of involvement of the project management and the way in which you use all the information you get from a PMP can be pretty different according to the company and the projects you're working.
Okay. Good stuff. So a lot of people listening are founders of space companies. They're looking for funding. And you have experience as an independent expert evaluator for the European Commission. looking at projects about future and emerging technologies. So I'm curious, from that experience, you did that for a couple of years. What was the biggest mistake or glaring omission that you saw in these research proposals that were submitted? I mean, what could folks do better to increase their chances of winning an award?
Yeah, let's say usually the proposals that we receive in the framework of these bids are pretty good because the people knows around that it's not so easy to get funded from the European Commission. On the other side, I think that especially in the field of future and emerging technologies, what sometimes I miss is or is not completely developed the way I sometimes would prefer to be, is this idea of the added value to the community in the long term. For example, usually these proposals are dealing really with focusing on the technical implementation of the idea. Say, okay, let's see, nobody has done this before, so this is very innovative. This is the real added value. But sometimes they dwell too much in the detailed description of the underlying physics, these kind of things, and they probably miss to describe the added value to the community. It's not necessarily the community, let's say, in your field of experience, but can be the community in a larger sense. And to provide some, especially to some reviewer like myself coming from the industry, this long-term view of the potential evolution and adoption of the concept. I mean, we're not necessarily looking at a return on investment in the short term or break even in 1 year or two, because this is not the topic of future emerging technologies. But still, I think it's giving a lot of points to proposals that can put together the technical aspects of innovation together with the view of a potential evolution of the addition market, potential implementation of the idea, and they also have a view of how the things will move in the future around their own idea. And I think this is our recommendation I would like to give to all the people, I mean, currently or in the future working on this kind of proposal, is not to, let's say, focus or not to leave this kind aside, because they are pretty much important for especially for the industry.
Okay, so unlike a PhD or master's thesis, you're not just adding to the sum total of human knowledge, but write down, where this baby can go. It's going to grow up, and what's it going to do when it grows up? Maybe some ideas about that. Okay, well, let's get into the electric propulsion systems for small satellites. If you could begin by explaining the concept so that we are all on the same page, that would be a great place to start.
Yeah, of course. So, well, electric propulsion is a kind of alternative to the in-space propulsion. So when we are talking about electric propulsion, we are talking about something which is already in space. So it's a satellite mainly, or a probe, but it's not a launcher. Okay. So the idea is that the reason for this is that electric propulsion is another way of giving thrust, so giving to push satellites, for example, but continuously. While, for example, on chemical thruster, which is the more conventional way of propelling satellites or even launchers, what you do basically, you give a lot of thrust all of a sudden, and then most of the time you leave your satellite to coast up to the final destination. So you have a lot of energy which is given right away to the satellite, and then you leave it along the orbit. Electric propulsion is the other way around. They do not provide a lot of thrust, but what they do is that they provide thrust all the time through till the final destination. So it means that over time, you are gently pushing your satellites all the time through. And at the time you reach your destination, you are probably much faster than with the chemical one, because you are keeping pushing. In space, you don't have, you don't have frictions, you don't have forces other than the gravitational forces.
Right.
So basically, you can accumulate this acceleration up to speeds that are dramatically high. And the way in which you do this is basically you take a certain propellant, which is usually stored in conventional electric propulsion system, is a gas, is a noble gas like xenon, krypton, argon, these kind of things. And instead of, let's say, breaking down the molecules as we do with the chemical propulsion system and getting the speed out of the energy of the molecules, here what we are doing is that we give energy to the propellant, and we make it ionized. So basically, we get an ion and an electron out of a neutral. And the idea is that through a combination of electric field or electromagnetic field, so a combination of electric and magnetic field, you accelerate ions. So these ions can be ejected at speeds that can be some tens of kilometers per second out of the thruster. So, and gave you a gentle thrust, because we are talking about, let's say, anywhere between micronewtons for very, very small thrusters up to 1 Newton max for a very big thruster. But you can do it with a very low consumption, let's say, which is a parameter which is called specific impulse. You can do it with a quantity of propellant which is dramatically less than a chemical thruster. So what's the advantage of this then? You know, first of all is mass, because if you don't have to bring a huge amount of propellant with you to do a certain amount of orbit, you can of course gain mass in your satellite. And mass is very, very critical, for example, for scientific missions. If you need to go to Saturn or to Mercury very fast, very far away, you cannot afford to bring super huge satellites, because with 90% of the satellite which you use for propellant, I mean, it makes no sense. On the other side, for small satellites and even more for big constellations, when you need to stack a lot of satellites in a launcher to reduce the number of launches to deploy your constellation, it's very, very useful to have electric propulsion, because of course, otherwise you will need to dedicate a lot of mass, and so a lot of launch capacity to the propellant and not to the payload. So what you really want, so the telecommunication payload, for example, the channels for your internet connections or for broadcasting. So electric propulsion basically can enable this kind of missions. So missions that are very far, like Dawn missions or Bepi Colombo that has been recently launched by the European Space Agency, that they are going very far away in space, or like constellation like OneWeb or SpaceX or future constellations. They are all based on electric propulsion for this reason. So when we talk about electric propulsion, it's a little bit difficult to, because it's a term in which inside you have everything. I mean, you can propel, for example, cubesats with electric propulsion. So we are talking about technologies that are very miniaturized. So we're talking about 100 grams electric propulsion system capable of doing 1 micronewton thrust, up to huge thrusters capable of running at 25 kilowatt, for example, or 30 kilowatt, and delivering 1 to 2 Newton thrust. So it's a huge, large number of product portfolio in the range of electric propulsion. And the electric propulsion on the other side is, it's another, say, key aspect with respect to chemical, is that they are intrinsically very connected to the design of a satellite. Chemical propulsion, basically, I mean, you can think about having this module which is attached to the satellite and is kind of standalone. Electric propulsion need to give power. So to give power to the electric propulsion, you need to have solar arrays. So these solar arrays, their sizing, their for example, reduction of the performance over time, their interaction between the plumes or the ions getting out from the thruster with the solar arrays, they're changing or reshaping the way in which to design the satellite. So it's not just that electric propulsion, you plug an electric propulsion system, that's it. It's much more than this.
Right. Yeah, many components inside the CubeSats are plug and play, easy things off the shelf to buy. But I think the propulsion, and as Dr. Rick Fleeter said in a previous episode, the attitude control and the propulsion are the two most complex systems on the thing. And here, what you're saying is that it's even more complicated because we have to redesign. So, I mean, it sounds great. We've got a way of increasing the payload mass instead of just using it up as more chemical propellant for the satellites. Most of your rocket is chemical propellant anyway, right? So any saving that we can have up there is good. Inside the smallsat or CubeSat, it takes up less space because it's just that gas there that we're taking the ions and pushing them out. And I imagine the continuous thrust, there's no air resistance like you were saying up there in space, obviously, and it can just keep pushing and pushing and increasing that acceleration. But because it's not going bang one time like a chemical thrust explosion, I imagine the stress on the components is lower as well.
Yes. Yeah. Okay. Stress on the components is lower in terms of, let's say, force, which is felt by the components themselves. Mm-hmm. However, for example, there are drawbacks of using electric propulsion, especially when we are talking about, for example, geostationary satellites. You need, for example, to go to geo starting from a low orbit. Mm-hmm. The time you need to spiral up to the geostationary orbit is much longer than a chemical thruster. With a chemical thruster, you may need 1 week to get there. With the electric propulsion system, you may take, I don't know, something like 6 months to get there. And within these 6 months, you need to cross the Van Allen belts. And since you are spiraling up, and you're not just moving there one shot, you go up and down, in and out the Van Allen belts. And this is creating a kind of stress, which is due to the radiation load. So it's not a stress due to the acceleration, but it's an environment effect that has to be taken into account when we are talking about electric propulsion, especially for this kind of application. Of course, there is another drawback, is using electric propulsion takes 6 months to get to geo. Geo is where the satellite is starting having a revenue generating phase. So, which is the trade-off between reducing the mass of the satellite, so having more payload capacity on station, against the fact that you will start having revenues 6 months, 4 months, 8 months after the launch. So this is a trade-off that big telecommunication operators, they have done. But what we see in the last few years that, I mean, almost all of them, they are now adopting electric propulsion solutions. So the trade-off seems to be resolved or move towards the direction of a use and adoption of electric propulsion rather than keep using chemical to get there.
Okay. So yeah, that was my question, is like, why wouldn't everyone move to this propulsion system then, as opposed to chemical? And the answer is certain applications. So a larger satellite, one that needs to be geostationary, probably not the best fit, because the CubeSat is only made to last a year or 3 or 4 or whatever. And if you're taking out 6 months of that as a chunk, that's a lot of time of the usefulness of the satellite that you've taken away, where it can't be doing its job and potentially bringing in revenue. So maybe
let's
not
say historically, For geosatellites, they started with a chemical propulsion to go to orbit, and then using electric propulsion to do on station. So, you know, when you are on station, from time to time, you have to keep your pointing toward the Earth, because otherwise your antenna will be depointed. And so these kind of maneuvers was the first application, commercial application of electric propulsion systems. So besides the scientific missions, this was the first application. So keeping the satellite on their in-orbit position. And this was very useful because you can do this by basically not consuming much of propellant, because the idea is there, when you are there, you want to be there without consuming, consuming as less as possible, because anyway, this kind of propellant is, in a sense, wasted to keep generating revenues.
Right. And but so, then, yeah, you want a soft pushing for these little adjustments to keep the antenna pointed the right way, or the camera pointed the right way, or whatever. You don't want these big, heavy thrust pushes.
And you don't want to spend too much for these small adjustments. But then in the last few years, things changed, because now we don't only do on station, so we don't only do this small adjustment, but really in the last few years we have witnesses the increase of these called AllElectric platforms. They are basically using only electric propulsion on board. So even doing the orbit raising, so moving from the injection point up to the geostationary orbit, they're using electric propulsion. So, all the major primes have sent or will send all-electric satellites for geostationary applications. So even if accounting for the delay in revenue generating, it seems that most of the time, at least something like 50% of the times, because this is more or less the share between electric and chemical for the orbit raising, there is an advantage of using electric propulsion rather than keep using chemical.
Okay. You seem to want to say something else, so go ahead.
Yeah, no, I'm saying that it's not that electric propulsion is the only electric propulsion system we have. There will be, and there is still, and will be room for chemical as well, of course.
Okay. Well, what new developments in that electrical propulsion field are you seeing coming up in the near future?
Well, there are plenty of them. To be honest, in the last few years, I think, spurred by the constellations, there's been a huge increase in number of startups and companies that are dealing with electric propulsion. Of course, most of them are mainly focusing on the CubeSat market, or on very small satellites, for different reasons, because of course there the volumes are bigger if we compare with huge governmental missions, for example, or scientific missions. But it's also because developing small propulsion system entails a cost, let's say a capital expenditure, which is significantly lower than developing large propulsion systems. Because, when you develop electric propulsion system, you need to test it, and usually the way which we tested it is putting them in vacuum. So you need to have a vacuum chamber that is, let's say, is creating the vacuum condition as close as possible to space. So of course, the chamber size goes with the thruster size. So, testing a big thruster will take a huge chamber, which costs a lot. Of course, small companies could not necessarily, let's say, afford to have that. So these new companies are exploring different technologies. So let's say the consolidated market is now focusing on two major technologies: the Hall effect thrusters and the ion thrusters. Hall effect thrusters are historically being developed by the Russians first, and then moved to the Western, to Western countries. And ion thruster is the way around. I mean, it's been mainly developed in the US and used by US companies for mainly. And these new companies, these startups we are seeing now, they are developing different kind of technologies. I mean, miniaturized field emission electric propulsion systems, or completely different type of technologies. So there are two ways in which the development I see is moving. Is on one side is the spurring of new technologies, mainly linked with very small satellites that cannot necessarily fit to biggest satellite because they are limited in terms of, for example, performance, or they're not necessarily fitting all the requirements we have with bigger platforms in terms of lifetime, in terms of trust level. On the other side, I see that the consolidated technologies are changing as well, not necessarily in terms of technology itself, but in a sense that they are moving towards the industrialization phase. So far, for example, we have not really had the need of ramping up production. Space was not necessarily a mass production environment. It's not like the automotive industry or the consumer market. Right. So, I mean, nobody was really pushed to have this idea of production in mind. So it was really like quality first all the time. And I'm not saying that full production is not quality. Full production is quality, even more quality, but it's a different way of doing it. It's a different way of implementing it and checking for quality. And what I see is that the innovation is for these consolidated technologies like AllElectric thruster and ion thruster is really much focused on production. So new way of producing, new way of design to cost, or design to manufacture, design to test, in order to gain even 1 hour, 2 hours of test to be able to ramp up production. So here, you know, when we're talking about the big constellation like SpaceX or OneWeb or Amazon, so we're talking about tens of units per day. So it's they are from zero to ready to flight. So this means that behind you need to have very strong way of produce, control the quality, have processes to know what to do in case you have an anomaly, so react very fast. So what I see is that there is a lot of cross-pollination between adjacent market like the automotive, like the aviation market. They are coming in to create innovation and improvements in the electric propulsion field. On the other side, I would be very, I'm very happy to see this growth of new technologies as well, because even though they are probably not directly plug and play to bigger satellites, they are certainly posing some very good seeds in the electric propulsion community. And I think that few of them, probably not all of them will survive, or not all of them will survive with the promise of huge volumes and big revenues. But I see that there is big opportunity, in fact, to implement these technologies, because even the market is changing. So, I mean, we will do more and more with CubeSats. This is my personal perspective. We will do more and more with smallsats as well. And so what we will ask, what we demand to the electric propulsion will change as well. So I see that at a certain point, we will need to have new technologies coming in. So that's I'm pretty excited to see how electric propulsion has evolved in the last few years, because I'm quite recent, if you want, in electric propulsion field, because I started in 2007. But when I started, so even if it's a few years ago, it was not at all the way it is now. Now it's really, really moving forward much faster, with a lot of ideas, a lot of companies that are investing. So huge amount of private capital, which is put it in this kind of concepts. So this is surely a good moment to be in the electric propulsion nowadays.
Well, great. I appreciate you talking about that process development, the manufacturing shift from job shop, we're going to make one custom big satellite, to a more continuous manufacturing operation like automotive, for example. That's exactly the kind of stuff that we do at Cold Star. That kind of process engineering, continuous improvement, the Six Sigma black belt stuff to make sure that the quality is great. That is exactly the kind of thing that I've been hoping to hear more about in the space field and bring to it. And so for you to say, look, here in the electrical propulsion field of space, we are adopting those ideas. That's very exciting to me. Well, Riccardo, thank you for being on here today. It was wonderful to have you as a guest.
Well, thank you. Thanks for this opportunity, and thanks to all the people on the other side of the TV.
Right. Yes. My guest today has been Dr. Riccardo Albertoni. He is in charge of the electrical propulsion systems program at Airbus.